NASA, the ESA, and the Canadian Space Agency, CSA, have collaborated since 1996 to define a successor to the Hubble Space Telescope, HST. The James Webb Space Telescope honors NASA's second administrator, James E. Webb, who headed the agency from February 1961 to October 1968 at the Apollo program. The telescope, which was primarily created to find life on exoplanets, has brought some new clues to help fulfill its mission. Welcome to Space Rumor. Today we're going to take a look at the James Webb Space Telescope's new clues on alien life. Searching for biosignatures. Researchers have figured out the biggest clue to catch a glimpse of life on other exoplanets. This clue involves the biosignature methane. According to scientists, the first hint humans may get of life beyond Earth might be methane. However, they need to be extra careful before declaring a discovery based on methane, and there are reasons for that. Basically, if an exoplanet's atmosphere contains methane, this could indicate a sign of life provided the planetary conditions meet specific criteria. For example, where the exoplanet is a small rocky planet orbiting a star like our Sun, the researchers found that atmospheric methane is more likely to be a biosignature if the planet meets three conditions. If there is also atmospheric carbon dioxide, if the atmosphere has more methane than carbon monoxide, and if the planet is not water-rich. According to Maggie Thompson, a researcher on the study, one molecule is not going to give you the answer. You have to take into account the planet's full context. Methane is one piece of the puzzle, but to determine if there is life on a planet, you have to consider its geochemistry, its interaction with its star, and the many processes that can affect a planet's atmosphere on geologic timescales. While methane has long been considered a potential biosignature, there are a number of non-biological processes that can produce the gas, from volcanic eruptions to asteroid impacts. So there are chances that when detections occur on exoplanets, they could be false positives when identifying atmospheric methane as a biosignature. However, the researchers at UC Santa Cruz are working toward ruling out such false positives. For example, outgassing from volcanoes would add methane to the atmosphere and carbon monoxide, whereas the biological creation of methane would likely consume carbon monoxide. Therefore, if an atmosphere has both large quantities of methane and carbon monoxide, the methane is not likely a biosignature. With the aid of NASA's James Webb Space Telescope, researchers will be able to study atmospheric methane in greater detail than any other potential biosignatures. This study is focused on the most obvious false positives for methane as a biosignature. Co-author Joshua Chrysantoton, an astrobiologist at UC Santa Cruz, said, "The atmospheres of rocky exoplanets will probably surprise us, and we need to be cautious in our interpretations." When will we find alien life? It's only been a couple of months since NASA launched the James Webb Space Telescope, the most powerful space telescope ever built, but there are many hopes for what the JWST will achieve. Astronomers are hoping that what Webb sees will change the way we understand our universe, just as the Hubble Space Telescope did decades before. However, unlike the Hubble, the JWST will be able to directly image planets orbiting distant stars and maybe, just maybe, detect signs of life. Over the years, the possibility of detecting biosignatures has been a topic of discussion. A discovery of this kind was recently found in our solar system. The phosphine in Venus's atmosphere sparked speculation that a microbial life form might create the chemistry. Also, experts have proposed that plant life that uses photosynthesis for energy could be detected in infrared wavelengths, as chlorophyll absorbs visible light but shows up brightly in infrared, and would give planets covered in foliage a distinct red edge. A single pixel photo of a distant planet just might contain enough information to tell us if biological life is there, based on the information stored in the wavelengths of light that reach the telescope lens. However, that isn't the only question. In fact, the most important questions are, what about intelligent life? Could JWST detect civilizations similar to ours? How would we look for them? the best answers come from understanding what humanity's presence on Earth looks like from outer space. Here on Earth, we give off waste heat and artificial light at night, but most significantly, we produce chemicals that fill our atmosphere with compounds that wouldn't otherwise be present. In other words, our biosignatures. These artificial atmospheric conditions just might be the thing that gives us a way to a distant alien species spanning the galaxy with their own powerful telescope. A recent paper examined the possibility of using JWST to search for industrial pollutants in the atmospheres of exoplanets. The paper focused specifically on chlorofluorocarbons, CFCs. On Earth, CFCs are produced industrially as refrigerants and cleaning agents. Back in the 80s, CFCs infamously created a massive hole in Earth's ozone layer, and it continued for 7 years before an international ban was placed. The ban helped reduce the level of CFCs back to less harmful levels. If these greenhouse agents with lengthy atmospheric residence times are found elsewhere in the galaxy, it will prove a civilization capable of rampant industrialization. In other words, humanity's pollution and some of the harsh byproducts serve as elements that make us detectable from outer space. This simply means that we may be able to find other species capable of treating their own planet's atmosphere with the same disregard. However, it is important to know that there are some limitations to the James Webb Space Telescope's CFC finding capabilities. For example, in a case where a planet's star is too bright, it will drown out the signal. Therefore, the telescope will have the most success by looking at M-class stars, which are dim, long-lived red dwarfs. A nearby example is TRAPPIST-1, a red dwarf 40 light-years away, with several Earth-sized planets orbiting within its habitable zone. JWST would be able to see CFCs on TRAPPIST-1's planets because the dim star won't drown out the CFC signature like a bright star like our Sun, a G-type star, would. Conversely, a JWST-like telescope at TRAPPIST-1 wouldn't be able to see Earth's CFCs. Our Sun is just too bright. Unfortunately, M-class stars are not usually conducive to life because when they are young, they are unstable, sending out powerful solar flares that might just exterminate any nascent life on nearby planets. However, they tend to calm down as they age, so it isn't an impossibility. Not your average telescope. A view of the James Webb Telescope on the outside shows glaring differences from its predecessor, Hubble. While Hubble is enclosed in a cylindrical tube that shields the optics from stray light, just like your everyday telescope, Webb utilizes a hexagonal shape to allow for a high filling factor and 6-fold symmetry. Depending on its position and its orbit, Hubble can be exposed to a lot of light blazing from the Sun in one direction, reflecting from the Earth's surface, or even coming off the Moon. Although it can handle large amounts of light, it pales in comparison to what Webb can handle. Webb is more fortunate. Seen from the L2 point, all these bright sources are in more or less the same direction, so all the telescope needs is a single large sun shield. Then, in the form of primary and secondary mirrors, the bare optics sit on top of this. The result at first glance looks more like a radio telescope than an optical one. However, in terms of function, both Webb and Hubble are constructed on the same principles. They're both built around a large primary mirror which has the crucial job of capturing as much light as possible from objects that may be on the very edge of the observable universe. So in essence, the bigger this mirror is, the better. In Hubble's case, it's 8 feet (2.4 meters) in diameter and made from a single circular piece of glass. If this was scaled up to the size needed for the JWST, around 21.3 feet (6.5 meters) across, then not only would it be extremely difficult to fabricate, but the result would be too large and heavy to launch into space, according to NASA. Mission objectives of the James Webb Space Telescope. One of the biggest questions of our human race is whether our civilization is the only one in existence. For decades, humans have been trying to uncover this mystery, and with the achievement of technology, we seem to be getting closer to answers. The primary objective of the James Webb Space Telescope is to discover life on exoplanets, but it can do far more than just that. The JWST's investigations will cover questions such as, what did the early universe look like? When did the first stars and galaxies emerge? How did the first galaxies evolve over time? What can we learn about dark matter and dark energy? How and where do stars form? What determines how many of them form and their individual masses? How do stars die, and how does their death impact the surrounding medium? Where and how do planetary systems form and evolve? In all, it will observe the universe's first galaxies, reveal the birth of stars and planets, and look for exoplanets with the potential for life. Whether we actually find life or simply the ingredients for life, the fact that we are about to have the capacity to look at all is a game changer. Do you think the James Webb Telescope will find life on its exoplanet targets? Let us know in the comments below. As always, thanks for watching Space Rumor.